Okay, thanks for joining me. I'm Jack Chandler. I will be presenting T-SGX, Eradicating Controlled Channel Attacks Against Enclave Programs. This is a fairly recent research paper revolving around computational computing that was published to NDSS in 2017. So the core idea of this is the privacy guarantees of computational computing. We're going to be looking at the Intel's solution, the software guard extensions known as SGX, and some of the side channel attacks that have been discovered to essentially be able to penetrate the protections guaranteed by the SGX. More specifically, we're going to be focusing on a controlled channel attack, which is just a specific type of a side channel attack, and how T-SGX is able to utilize Intel's other computing feature, the transactional synchronization extensions, TSX, to be able to mitigate these controlled channels. What's always important to keep in mind is the performance and security trade-off, where as we're going through any type of security implementation, there's going to be significant performance overhead, which may make the design and implementation not practical for real use. To begin, let's consider a simple use case. Let's look at a cloud-deployed machine learning model. So a simple model might perform classification off of an image. So if we take our image on the left, a pig, run it through some neural network model, it will return out a classification for the image, in this case, a pig. In a simple example like this, we might not care about the privacy of the input data, the model itself, or the output data. However, if we were to consider an example where user confidential data were to be employed, then there might be restrictions on what we're able to do based off of the security of the system. You may also consider this for the model IP itself, where the intellectual property of the model should be protected. This is going to introduce our first concept for security, which is confidentiality. We want to ensure that the input data that we're passing off to a cloud deployed system, where we may not be able to trust the cloud maintainers or servers or hardware, and we need to guarantee that the input data and procedures that we're using won't be leaked or publicly available. Of course, in an actual application, we'll also care about how it actually runs and the successful output that it returns. So another concept that we need to consider is integrity. We expect that our deployed program will be running accurately and returning the valid results that it intends to, whereas this might not be the case if an attacker were to be manipulating and controlling the system. A high-level overview of computing security would include a multitude of threats, and these can be attacking a variety of surfaces in the actual deployed model. So if we think about our use case for a cloud-deployed machine learning model, these threats could be attacking the host servers themselves. They could be co-tenants that are trying to modify or manipulate other running programs from other users, or it could be attacking our system itself directly. There are different protection strategies which seek to provide guarantees against these threats. The first of this is computational computing. This is generally a hardware-based approach which will use specific hardware resources to guarantee the confidential execution and perhaps integrity of running programs. Multi-party computation is another. In this strategy, multiple different servers or parties can cooperate to compute a result while each party does not know the exact data that's being input to it. Homomorphic encryption is an idea to enable the computation over the encrypted data, which can, of course, provide security guarantees, but often comes at a significant performance cost. Another idea for protection would be a trusted platform module. This could be something that like an external component, which will have built-in verification guarantees. If we look at a generic cloud hardware platform, what we'll see is a number of server blades, and each of these will contain essentially its own computer. This will entail the CPU, which connects to memory and storage, and any number of peripherals such as a GPU, a NIC for network communication, and I/O. Now, the important question to ask, if you are an outside user that's going to be using this cloud platform, what can you really trust going in and deploying your code on this unknown server maintained by an unknown party? There can certainly be trust already existing between the client and the provider, but there's always potential opportunities or risks that could lead to attacks both on the hardware level and software level. This is where we introduce the concept of the Trusted Computing Base, or TCB. In an untrusted setting, a client may be deploying code and applications with expected trust of the remote server. And this might be depicted on the left, the largest box in this diagram, where a trusted application would be running with a potentially trusted VM, if applicable, which would be then run on top of a trusted OS and hypervisor on top of all of the trusted hardware components. This is placing trust in a variety of cloud-provided amenities, including co-tenants, which may also be running code on the host. A strategy to mitigating this would be confidential VMs. In this case, we could be running a trusted application and guest OS on top of a VM, which we trust in the host of that cloud provider. And that would again be running on top of trusted hardware features. The perhaps strictest of the three here is going to be confidential computing, where we have a trusted application which is running without any trust placed into the OS or VM, but will still require some amount of trust on the hardware components to be able to effectively provide confidential guarantees. This is where we get the concept of the Trusted Execution Environment, or TEE. If we think of our example, we have a client which is providing both data and code to a cloud, which will then run this application. Data in transit will already be expected to be encrypted. However, the data privacy practices of the cloud provider will not be guaranteed. In a TEE, we will restrict the trust on the cloud provider solely to the CPU chip that is going to be running our program. Within this chip, the data in use can be unencrypted and safely run. However, any data off the chip, say going to an untrusted GPU, memory, or computer storage, would all need to be encrypted. If we expand this idea to the software level, we will see that we have some application running on the guest operating system, and only within this application is our data in use going to be unencrypted, and with the hardware guarantees provided by the CPU chip, we can guarantee that no other running applications or the operating system will be able to directly use and manipulate these values. On a hardware level, again, is solely placing trust in the CPU chip. All of the connected peripherals that are untrusted will not be able to directly use this data. Employing this idea are secure enclaves. The example that is the focus of this paper is Intel SGX. With SGX, you can design an application to include a specific enclave component where the code and data will all be protected and only accessible by the CPU chip. Another example is the ARM Trust Zone, which is widely deployed in a number of mobile and tablet applications. This operates slightly differently, but still retains a confidential boundary between secure computation and other applications. Now, to highlight the features of these TEEs, the first of which is going to be the runtime encryption. Basically, everything that is off of the central CPU chip, our TCB, is going to be encrypted and therefore protected from external probing. Another feature is going to be isolation. So in the case where you have co-tenants, other users running on your same cloud server, they will not be able to modify or interfere with the execution of your program. And perhaps critically, for the guarantee that this is actually being run correctly, is remote attestation. What attestation is a process by which you can verify that the TE is configured and correctly running your application. Without this, you would not be able to guarantee the initial state of the remote asset, and therefore you would not really be able to guarantee that your code has been correctly assembled and able to run. In the untrusted cloud, of course, there's not going to be protection. In the TEE, we now have protection for other workloads, but there may still be threats from the cloud provider. A more ideal scenario might be when a third party can provide a trusted attestation. This way, as long as there's no cooperation between the cloud provider and the third party, you can guarantee that the attestation is correct, which will then guarantee that you have correctly initialized your enclave, and therefore your code and data will be protected. If we consider the threat model for this scenario, we can assume that an attacker will have physical authenticated machine access. In a cloud setting, we can assume that an attacker will have physical authenticated machine access. They could be running other programs, or running a malicious OS, performing snooping on the hardware components, as well as running cold boot attacks on the memory of your server. This is why the trusted computing base in our scenario is solely restricted to the CPU chip. Everything outside of this chip is assumed to be untrusted. An important note here is that this is pushing the trust from the cloud provider down to the hardware manufacturer, which would be assumed to be producing the correct hardware components to enable this trusted enclave. Another flavor of privacy-preserving computing that I mentioned is conventional virtual machines. There's a variety of examples in practice for this, and you can see that this slightly increases the attack surface. So if we look at the image, without conventional computing, of course, the entire system is at risk for an attacker. With conventional VMs, we are supplying a guest OS and application, which is going to be running on a trusted CPU. How Intel SGX differs is that we are providing a portion of the app that is designed specifically to run with the protection provided by the enclave. So we've built up this entire conventional computing world, but how can we actually attack these systems? An emerging issue with these has been side channel attacks. Side channels are really any medium where you can measure information about the ongoing system. Some examples would include a timing-based attack, where if you were to measure the time it takes for a response for a given input, you might be able to infer something about the process or data. Another example will be cache-based, where you can monitor the cache usage to track memory locations. Shown in the image below is a power analysis graph, where you can actually track the DES encryption algorithm based off of the power fluctuations, the voltage fluctuation over time. What this paper is looking at is controlled channels. Now this is where an attacker may have specific control over this channel and may induce certain events in order to trigger information spilling out into the channel. The most prominent for this case would be a page fault, where traditionally in a computer there's going to be a number of virtual addresses which point to physical addresses in the memory as well as locations on the disk storage. Now of course the entire disk won't be able to fit into memory, so the workaround is to use page faults. When an address is requested but is not loaded into the current memory, it's going to have to request it from the disk, which is a tracked event in the CPU. Now this is where it introduces a potential issue where an attacker can try to induce page faults and then probe for memory location accesses, thereby gaining information about the location of the memories used by the victim program. Another example for a control channel attack would be an interrupt-based attack, where essentially you can suspend the execution of an executing program in order to be able to track its current hardware usage. The page fault is the focus of the T-SGX defense. A little more detail on the page fault and its capabilities includes extracting documents as well as probing into ASLR, a address space randomization, to avoid memory probing events. The requirements are not difficult to achieve. It only requires the run of the victim code and for the user to have page table access, which if we have a co-tenant or given our threat model, an attacker with authorized physical access will be no problem. This strategy was proven to be effective against several leading security implementations, Haven and Enclave. Haven's strategy developed an interface between the Enclave and the host to provide an additional barrier, but was still susceptible to leaking memory locations. There are, of course, defenses proposed to sort of mitigate these attacks. However, they may come with additional costs. A simple example will be an obfuscated memory access. If we can sufficiently obfuscate the memory access or make it very unclear or an irregular what memory addresses are actually being accessed, it would be very difficult for an attacker to then be able to extract the important documents. The example image shown models a sort of ORAM tree fashion where memory accesses will be accessing multiple different addresses, and after reshuffling, will be very difficult to track by a third party. The cost of this, of course, is going to be the large overhead in additional processing and memory access times. Another example of defense is self-paging. This is a smart idea to handle the page faults in the Enclave level instead of at the OS, thereby circumventing the OS inspection of which pages are being accessed during a page fault. However, this is going to require specific hardware accommodation, which at the time was not commercially available. So, if we're trying to protect our confidential image of a pig, how can we mitigate these side-channel attacks to improve our use of confidential computing? T-SGX proposes an implementation to utilize the already existing T-SGX. Its strategy will be to identify the events of page faults, and if it's able to successfully do so, it can mitigate their effect. The first major component of this is the Intel T-SGX. T-SGX enables synchronized hardware events, which we will use for code blocks of our application. In the example code provided, we can see that a simple function can be transformed into a protected function. What's required here is that it will begin a transaction. It will create a transaction with the given code block. If it's not able to do so, it will abort. T-SGX essentially enables an atomic operation. Atomic would mean that it's effectively operated in a single cycle, in a single clock cycle, and therefore unable to be interrupted by a fault attack. T-SGX revolves around this T-SGX transaction. It includes first a springboard. What this is another memory region which will call our transaction blocks. And the point of this region is that it may be leaked over the page fault channels, but it will not be containing anything confidential. The springboard calls the transaction block, which will execute the given program. T-SGX goes into a number of optimizations in order to improve these executions, which I will not go into. Critically, T-SGX will abort given an exception, which can remove the transaction block and pass to the kernel space for exception handling. Recall the trade-off that is the center point of security and computing, that is the privacy and performance. If the security measure is very inefficient, it will be very impractical for real use. The T-SGX includes a number of optimizations which were designed to improve this. The image on the left is demonstrating a high number of instructions included in each execution block, which therefore improves the throughput by number of transaction block. Each transaction block call will be incurring its own overhead, so increasing this number will be decreasing the performance hit caused by the number of transaction blocks. It's important to note that the T-SGX aborting could potentially be an issue. However, from their experimental design, for the majority of transaction blocks, the number of aborts was 0, and it never exceeded 3. Another factor for practical use is going to be the scalability, how well this can translate to larger systems. T-SGX was shown to maintain a significant improvement over the baseline. regardless of the number of instances running. As perhaps expected with security issues, there's going to be open problems with this design. The first is that T-SGX is an imperfect leakage prevention. Recall the springboard, which is a potentially leaked area of memory. Additionally, T-SGX is designed to cover the specific controlled channel attack. Other attacks, even the cache controlled channel timing attack, can still be effective in this scheme. Other factors such as memory bus snooping were an unresolved point discussed in the paper. And breaking down SGX, TSX was shown to have side channel attacks, which could make TSGX vulnerable. Because the design is dependent on the TSX hardware support, its use is limited to those devices that can run TSX, which has been deprecated in certain CPU lines. This concludes the presentation of the T-SGX, Eradicating Controlled Channel Attacks against Enclave programs. Thank you for your time, and let me know if you have any questions.